yeah, I'm gonna tell you about neural autoregressive toolbox for many body physics. It's quite related to some of the topics Giuseppe discussed already. So yeah, I'm from Vector Institute, and these are the institutions supporting my research. Yeah, and I'd like to thank the organizers for the invitation. Sorry about that. Let me tell you what are autoregressive models, even though Giuseppe already give you a summary. So the term autoregressive originates from the literature on time series models, where observations from a previous time step are used to predict the value of the current time step. So that's very generic, but let me tell you about probabilistic autoregressive models, where we have a probability distribution P of sigma, where sigma is a vector of, let's say, discrete variable sigma I, where sigma I takes values from 0 to d minus 1. So the term autoregressive applies here if we rewrite this distribution in terms of the chain rule, where we write down this probability distribution as a product of conditionals, right? So here we have P of sigma 1 times P of sigma 2 conditional 1, P of sigma 3 conditional 1 and 2, and so on. And then the autoregressive part is that you can see it in this conditional here, that the probability of spin 3 or variable sigma 3 depends on the previous two, right? Like sigma 1 and sigma 2. I'd like to highlight a couple of things that to specify P in tabular form, either directly on the joint or the conditional requires exponential resources, right? And the insight from the machine learning community and from many people is that we can instead parametrize the conditionals to reduce this this exponential intractability. And so you introduce a model P theta for each of these conditionals, for instance. And so what are the advantages of doing this or having these probabilistic models? And I mean, already Giuseppe discussed this. They can be exactly sampled in polynomial time. And we use this in all of the examples that I'm going to talk about. Computing the probability of a configuration is always efficient if the number of parameters in the model doesn't scale with the size of the system in a bad way. They can be defined in any spatial dimension. And one thing that I would like to highlight is that this probabilistic autoregressive models contain mean field theories, right? Like, so for instance, if you're thinking about them as a quantum states, they contain, for instance, a very popular wave function called Gutzwiller mean field theory. So on top of that, you can impose symmetries and other inductive biases. So what are the disadvantages? And I have here like a question mark, is that for you to have expectation value over the distribution or over the amplitude, the wave function square, you require sampling to compute observables and gradients. So that leads to an error bar in the estimations of the gradients and so on. And this is, I wrote here this because usually, for instance, if you have some families of tensor networks where you don't, where all these advantages are also supplemented with the advantage that you can get expectation values in an exact form, so without sampling. But in spite of that, these are very powerful and very useful. I'm going to try to convince you that this is the case. The other thing that I'd like to highlight is that these three properties or these advantages remain true for autoregressive models of the quantum state, some of which Giuseppe already discussed, but I'm going to introduce a set of different ways of parameterizing the quantum state using these models that rely on a little bit of a different property. So what's a canonical example of a probabilistic autoregressive model is the recurrent neural network. So it's very common in machine learning, and basically what they do is what I already said, which is recurrent neural nets parameterize the conditional in the chain rule that I was explaining before. And the building block of recurrent neural net is the recurrent cell, which I have here graphically in green, and is basically a nonlinear function, right? Like which takes input vector hn minus 1 and some configuration or spin configuration sigma n minus 1. And through these parameters w and vector b, you compute the new vector, right? Like, so here is the recurrence part of the recurrent neural net. And based on that, you compute the probability or the conditional probability through yet another nonlinear function. In this case, I'm going to pick the softmax because I'm going to be dealing with discrete distributions. And so you apply this so-called softmax, and you add some new parameters w and vector c, and this is your conditional, right? Like through this vector y. Again, the sampling is as Giuseppe described it. You sample each conditional, and then you take whatever outcome you got, and then you feed it back again to the recurrent neural net through this object here, and so on. You do this repeatedly for each of the conditionals, and that's how you get this efficient sampling. And this is very useful for all these things that we do. So one thing I would like to highlight is that the RNNs are universal function approximators, and this has been proven in these papers, and some of them are even Turing complete. So I mentioned this is a toolbox, and there are many more autoregressive models like transformers, which were already brought up in the last talk, the neural autoregressive density estimator, autoregressive flows, pixel RNN, pixel CNN, WaveNet. There's many more, and the list is long, and all these models are very powerful and interesting. So the question I'd like to kind of like motivate is why to use these machine learning models for physics, because in principle this could fail, right? But what I'd like to highlight two points which I think are important, and is the dimensionality of quantum systems and the dimensionality of the systems people care about in machine learning, and in particular neural machine translation, which is one of the places where recurrent neural nets and transformers and autoregressive models are really powerful and has been explored, even though they have been explored also in computer vision and so on. But let me highlight the idea. The idea is that for a 2D, like a wave function is specified through a vector with 2 to the n components, if you're talking about spin 1/2 particles, and where n is the number of spin in your system. And so it's exponentially big. And it's just so big that today's best supercomputers can solve the wave function exactly only for about, say, 45 spins, because 2 to the n for that 45 spins already is a big number, and you cannot even accommodate this wave function in a supercomputer anymore past 45 spins, or around 45 spin. And I'd like to compare it here with the language translation models, which live in also in very high dimensional spaces. And this is an example from a paper where they introduced this transformer architecture, and it's called "Attention is All You Need." It's a very interesting paper. And the count is that the local Hilbert space, or if you want, the vocabulary size that you use when you're describing a sentence, plays the role of the local Hilbert space, which is in this case is 2 for spin 1/2 systems. So you have this vocabulary size, and then you have the maximum length of a sentence, which let's say it's a paragraph with 100 words. So you have 100, but the vocabulary size are very big, right? Like, so for instance, in like, I think this is an example that I read around, is that if you want to have a clear understanding of a paper or an article in the BBC News, you need about 8,000 or like roughly 8,000 words to have a good grasp. And then you power that to 100, which is for understanding a paragraph, and that gives you a very large state space where these models live. So that's, if you want, a commonality between these two systems, or between quantum physics and neural machine translation. The good news is both quantum physics and neural machine translation deal with problems with a lot of structure. So you know that even though these states live in very high dimensional spaces, like the relevant states of interest live in a much more lower dimensional space. And so we need to use this structure to be able to make progress both in quantum physics and in machine learning. and it's because there's a lot of correlations and symmetries. And the cool thing is that they have strikingly similar structure, both in machine learning and in quantum physics. So beyond high dimensionality, there's a lot of common structure, like, for instance, critical correlations, like those occurring in natural language and natural image and music. So all of which exhibit power law decay correlations, which are very similar, for instance, to classical and quantum many-body systems tuned, I'd say, at a critical point. The other aspect that is important is that the symmetry, right? And for instance, you can have translational, rotational, reflection, and other symmetries. And like if you want, the exploiting of this facts or this symmetries in the model drastically improve the sample complexity of the algorithms in machine learning, but also the computational complexity of the problems we deal with in quantum physics. So those we would like to exploit. So let me get to the content. So I'm gonna go a little bit in a different direction. Like, I'm gonna be talking about a probabilistic simulation of quantum mechanics. And this is motivated in part because of the issues with the signs that Giuseppe was discussing at the end of his talk. So I'm gonna give you two examples. So one is reconstructing quantum states with autoregressive models, and the second one is how to simulate quantum dynamics, or in this case, quantum circuits with autoregressive models. And instead of extending them to, say, wave functions and making them complex, I'm going to be rewriting quantum mechanics such that it looks more like a probabilistic model. Okay, so it's kind of like a little bit of a different approach. So, how do you simulate quantum mechanics with probability? So that's the question. And why do I ask this question? As I said, it's in part because of these challenges that appear when you're trying to optimize and to express the sign structure of the wave function, but also because this was an interesting question, at least in the 80s, right? So Feynman has this paper where he proposed simulating physics with quantum computers. So basically motivated the field of quantum computing, in which we hope to revolutionize computation through exploitation of quantum mechanical effects. So this is a seminal paper. It's not really a paper, it was more like a keynote speech in the 1980s by Feynman, where this idea of quantum computers was introduced. But in this paper, there's also this question in section 5, which is, can quantum systems be probabilistically simulated in a classical computer or by a classical computer? And he answered the question as a no. And this is still basically true today. So we still think that the answer is no. We cannot use probability to simulate quantum systems. And this is fundamentally linked to the notion of quantum speed up in quantum computing. But nevertheless, I was fascinated by this question. And if you want, what I'm going to tell you about is a modern formulation of this question based on machine learning or artificial intelligence, right? So we still think the answer is no, but can we do it approximately, right? Like, can we have an approximate simulation of quantum dynamics using autoregressive models? So that's what I'm going to focus on right now. So how is a quantum state traditionally described? So it's described through a matrix. It's called a density matrix, which describes the statistical state of a system in quantum mechanics. So everything we can possibly know about a quantum system is encoded in this matrix. It's a positive semi-definite Hermitian operator of trace 1 and acts on this gigantic Hilbert space. And this family of density matrices form a convex set. It's, for one qubit is this well-known block sphere, and that's the traditional view, right? Like, I'm going to introduce a different view, which is quantum mechanics just using probability. Okay. So how to do that? So we consider measurements, right? So when you go to the lab, you prepare an experiment on a quantum device, you measure it, right? And then you start getting outcomes, right? Like, you get outcome A1, A2, and so on. But these outcomes come with a probability distribution, right? Like, they come distributed according to some distribution, and this distribution is called PA. And the operators, the measurements that you apply on the system are described by operators MA. And these operators have some properties. They're positive semi-definite, and they adapt to the identity. Okay, so that's the idea that I'm going to exploit. So there's a Born rule then, on the other hand, which relates quantum theory and the experiment, right? So you create an experiment where you prepare state rho, and then you apply measurement operator MA, and then you get outcome A. And the probability of observing that outcome is P, okay? And that was given by Born, right? Like Born basically came up with this rule out of his pocket, but it works, right? Like it's the most important relation linking theory and experiment. I'm going to use a particular set of operators, MA. They're called informationally complete. And what that means is that the measurement statistics P contains all the information about the quantum state rho. That's the most important thing that I'm going to talk about. And that implies that the relation between rho and P can be inverted. Okay, so meaning that if I give you rho, I can also give you P, and you have the same information. And that's, if you want, how I represent the quantum state just using probability. And to construct this measurement, what I do is I take products of informationally complete measurements, and that's how I construct these measurements. And the cool thing about this is that then if the informational so the measurement is informationally complete, this relation can be inverted, and this is the expression for the inverse is given in terms of the probability distribution and the measurement. So that's the most important thing I'm going to say, and it's the only thing that I care about. But once you do that, everything about quantum physics follows, right? Like, so unitary evolution, Schrödinger equation, Lindblad equation, measurements, and so on. So here's, for instance, this Liouville-von Neumann equation. Once you apply this rule that I was explaining, then you get a differential equation for the probability distribution representing the quantum state. Okay, so that's the important thing. The insight we had was, okay, we can parametrize the statistics of the measurement PA using autoregressive models, right? Like that was what I wanted to do. So we will consider recurrent neural nets and transformers and so on. And as we said, we can have exact sampling, tractable density, and so on. And so the model for the density matrix is basically a probabilistic model, neural autoregressive model, contracted with some tensors, okay, which handle, if you want, the quantum part of the quantum state. We can also see this as a factorization of the quantum state in terms of probability distribution and some simple tensors that are that are, if you want, specified by how I measure the state. And note that all the complexity of the quantum state and the potential tractability of what we're trying to do is in the probabilistic distribution, because the rest of the state is, if you want, factorized. So let me show one example, like learning quantum state from measurements, which is, if you want, the closest thing to unsupervised learning, like generative modeling, right? So, and why we do this? Because we need to go beyond standard quantum state tomography. So, which is reconstructing a quantum state to verify that your quantum simulator is working appropriately, right? And so how it works is you prepare the quantum state that is unknown, and then you apply these measurements M on the state such that you probe enough information about the quantum state. And you repeat this on and on until you collect enough statistics about the state. And then what we do is we infer a reconstruction raw star using, again, these recurrent neural nets. And this was a paper that we published last year in February, where we used this idea of recurrent neural nets for quantum states. And so let me show you a couple of examples. So this is reconstructing the quantum state of a synthetically generated system. This is called the translatio model in one dimension with 50 spins. And so green, red is this synthetic state we generated numerically using DMRG, density matrix renormalization group. And the green are correlation functions obtained from our recurrent neural net wave function or language model that we use for the reconstruction. As you see, there's a good agreement between the expectation value of the sigma x operator at the different sites along the 50 spin chain And so there's a good reconstruction accuracy, as you can see from the correlation functions. So this is two-body correlation functions. And again, sigma 1 sigma I for the Z component of the spin. And then you see again a good agreement with the between the reconstructed state and the synthetic one. This is again in 1D, and 2D we tried and we see again good agreement. So this is an interesting system. It's the Heisenberg model in 2D on a triangular lattice, which has a complicated sign structure. We wanted to explore that because the wave function has complex, it has positive and negative values. And so we wanted to verify that this factorization, where you have a positive parameterized in the state, multiply or contracted with the tensors produces results even in those cases where the wave function is complicated. But we wanted more. We wanted to see if we can study real-time dynamics, and we picked this problem, which is simulating quantum circuits, again with the autoregressive models. So how do you translate quantum computations or quantum circuits into this probabilistic language? So it's in the traditional language is unitary rotation of the density matrix. And when you do this game of writing everything in terms of probability distribution, what you get is this equation. So you start from an initial probability distribution PA, and then you multiply it by a matrix, and you get your rotated distribution. So this matrix is very special. It's obviously related to the unitary that you apply in the state, but it has some interesting properties. So mathematicians call this matrices somewhat stochastic matrices or quasi-stochastic matrices, because if you sum over the columns, you get you get 1, but they can be positive and negative, and so they cannot be interpreted as a transition matrix in probability or as a conditional distribution. And so we have to be smart about how we get this PU. So what is a quantum circuit? Is just you start a quantum state in, say, a product state, like the 0, 0, 0 product state, and then you apply unitary matrices that are local. And then at the end, you measure the system. And that's how you perform quantum computations. And this is what a general quantum computation is. And the quantum algorithm is your choice of unitary matrices that you apply. And hopefully at the end, when you measure, you're solving some computational problems. So that's, if you want a summary of quantum computing, very fast. And this looks like this in the traditional setting. So you initialize this state at the zeros. So that's called rho 0. And then you rotate this state using these unitaries. So when you do this game, you get this. So you start from a probability distribution that is very simple. It's a product distribution. And then you apply this quasi-stochastic matrices until you get this time-evolved distribution or unitarily evolved distribution. The other cool thing about these matrices is they're also unitary and invertible, of course. And so how can we simulate quantum circuits with these models? So we have this initial distribution upon which we want to apply this matrix O to get this probability of this rotated distribution PU. So how to do it, right? Like that's the question. So the idea is we introduce a model P theta, okay, that is going to parameterize the outcome distribution PU. And what we do is very simple, as the simplest thing we tried. We compute the divergence between the PU and P theta, and then we minimize this divergence or minimize this distance, right? Like, so we took the KL divergence between PU and our model, and which we split into cross entropy and the entropy of the PU. So the entropy of PU is independent of the parameters of the model. So all we care about, at least for optimization, is this cross entropy term. So this term has, once you plug this expression in, you have two sums. So 1 over A prime, which we do through sampling from the model or from the distribution, the initial distribution. And then the second one, we perform exactly, and this is due to the fact that these gates are local, okay? So that's important, but nevertheless, so the key issue or the key message here is that this cross entropy can be computed through samples. And the second sum is only polynomial in the size of the gate, if you want. So if you have a 1 qubit gate, it's just a few order 1 A's. If you have 2 qubit gates, then it's a little bit bigger, but also of the order of 1. And then we minimize this cross entropy and search from a model p theta that approximates pu well. So this is the simplest implementation we had, but we do better in our paper. We introduce some variance reduction techniques and so on, so to improve the calculations of the gradient and so on, so to be better. And then now, if you have multiple gates, what you do is you repeat. You start from P0, you approximate with P theta 1. You try to be as close as possible to P1, but you can't. So, or hopefully, I mean, you get very, very close, but you're not doing this exactly. So that makes the technique a heuristic. And then you apply the second gate, and then you try to approximate this probability distribution P2 that is hopefully P2E, which is hopefully very close to P2. But then you get P theta 2 because you make a mistake and so on. So that's how we do it. And the hope is at the end, P3 is going to be very similar to P theta 3. That's the hope. But errors will accumulate since the training is not performed exactly. Okay, so that's how we perform our simulation. It's a simulation of a quantum computer using just probability. We had some examples. So we computed 2 simple states. One is called the GHZ state, which is prototypical example of an entangled state in quantum information. As basically these gates. We took this for 2 reasons, or we took two examples for 2 reasons. So one is that the number of gates is polynomial in the size of the system. So if you have n qubits, you have n gates. The other reason is that there's an efficient representation of the GHZ state for large systems, so that we can benchmark our technique for large systems. And the same is true for this linear graph state. And they're both entangled states. So meaning that we can simulate systems with entanglement. And this is the training dynamics for 2 qubits. So the simplest example. And what we see is that the scale divergence goes exponentially fast to very small, to numbers of the order of 10 to the minus 8. So as applying the first gate, and when we apply the second gate, which is this control X gate, we initially go exponentially, but then we have an error. And this error, as you see, is bigger than in the first step, meaning that this intuition that I was having, that the errors are accumulating, it's true. And this is the classical infidelity, where the classical fidelity is, I think in statistics, people call this the Bhattacharya coefficient. And if you do 1 minus that number, this number goes again exponentially to 0 initially, and then kind of like oscillates. This is L1 norm distance between these distributions, and what we observe is good convergence, so fast convergence to what we're trying to the state that we're trying to reach. And this is the quantum fidelity of the state. So that and these observations are reproduced also in this state. Then what we did was we wanted to scale to large number of qubits. We went up to 60 qubits. And as we see, as we grow the size of the system, the fidelity that is very good when we have, say, 10 qubits is worse when we have 60, meaning that this accumulation of errors as we apply more and more gates is the right picture to see, which is very similar to what happens in quantum computing. In quantum computing, as we apply each gate, we have errors. So in this case, there are numerical errors in a quantum computer, noise and decoherence, right? But this idea is very similar. Here I'd like to highlight 2 examples. So for the graph state, they have the current blue. This is with a transformer architecture and with a hidden state of size 16. So very small transformer. And what I see is that when we increase the size of the transformer to say 32, the fidelity improves, meaning that there's hope that we can start systematically improving the simulations as we grow the size of the transformer. So that is almost it. So I wanted to talk about recurrent neural network wave functions, which if you want, it's very close to what Giuseppe described. So he bid us to publishing this recurrent or this autoregressive wave functions, but I think I don't have time. So, but this, I'd like to highlight, this is the work of my PhD student, Mohammed Hibat Allah. And what I wanted to say is that we defined these wave functions that are basically based on the recurrent neural network, and we find really, really accurate results. And the other thing is we were able to introduce symmetry, like this local symmetry, spin inversion, mirror reflection, conservation of magnetization, and we were also able to impose Marshall sign rules and so on, but I don't have time to discuss that. So, and we also look at two-dimensional systems and compare with DMRG, one-dimensional recurrent neural nets, and two-dimensional ones, and a pixel CNN from Giuseppe. With that, let me conclude. So what's in this neural autoregressive toolbox? So we have two examples that I described in detail. So quantum state reconstruction with recurrent neural nets, which is this paper here that we published last year. The simulation of quantum circuits here that I explained. We have also experimental demonstration of the reconstruction scheme that we developed here. We posted on the archive recently with Cornell collaborators. This is the paper by my student Mohammed, recurrent neural network wave function. We have also transfer learning based on physical principles. This is coming soon, so we apply neural simulated annealing. So we came up with a way of doing simulated annealing using wave functions and for classical simulated annealing. And what we see is that we beat path integral quantum Monte Carlo and simulated annealing for Sherrington, Kirkpatrick, and we shared spin class problems. And we have a lot more, and that I'm excited about this type of models and their applications to quantum physics. And with that, I'd like to conclude. Thank you.
Thank you. We are also excited. Thank you very much for your talk.
Thank you.
So, good. It's been a long day. Are there questions or comments that somebody wants to make? Just maybe I have a generic question, which is in this series of works, do you have any idea of models which could realize quantum supremacy, could represent quantum supremacy, at least with respect to the class of classical stochastic process algorithms? I don't know if it makes sense, but
yeah. So I've thought about this a little bit. I mean, like, I think so. This quantum supremacy, at least the quantum supremacy experiment from Google. So this has very strong theoretical guarantees that this is very difficult to represent. It's basically what they're trying to do is they're trying to construct a state that is random in Hilbert space. Okay, so by definition, you have an exponential amount of information in those states. So I think it's very hard. Of course, when you add noise, then you simplify the simulation, and people have like been trying to simulate this quantum states using tensor networks, and they're successful, right? Like, so meaning that they can get simulation with equivalent fidelity with respect to those simulations, this quantum, like the simulations in the quantum supremacy experiment. So I would say tensor networks, maybe neural nets, but I haven't tried in this regime. So I tried this quantum computational simulations, which are at the scale of the quantum supremacy experiment in terms of the size of the system, but the depth of the circuits they looked at is way deeper than what I've explored. Of course, I was trying to have a higher fidelity simulation, and they have very low, right? Like, so I still have to see if by simulating this system with lower fidelity, I can reach the scale of like depth. They and yeah, I don't know if I answered the question, but
no, it's fine. Yeah, very interesting. Bert, you want to ask something?
Yeah. Hi, Juan.
Hi, Bert.
Hi. So I'm intrigued about this this mapping from density matrices to probability vectors, and you say this is invertible in some cases, but I presume it's not always invertible. And can you say something about that?
So yeah. So it depends on how you pick your measurement. Okay. So if you pick an informationally complete measurement that is called tight, meaning that you don't have more information than what you need, then you can always invert.
But so for a single spin, for instance, what would you measure?
So for instance, you would measure the Pauli operators along at least 4 directions in the block sphere. And then you're 4. Yeah, 4 is the minimum number. It's kind of like you can see it as a counting argument, right? Like from the number of elements you have in the density matrix, how many probabilities or how many numbers in the probability distribution you need to encode those numbers, right? But this is always possible. Like we know we can construct.
You only need 3 numbers, right? Because you only need the M vector, the magnetization vector for a single spin.
So you need so when you expand the density matrix of 1 qubit, you need 4 like the basis is the identity and 3 Pauli matrices, right? But there are complex numbers, right? Like so they're not just real, and you're mapping them onto probability.
But you can represent it always by 3 numbers. So it's a well, okay, never mind. So there's a bunch of let's go into detail. But anyway, so you say that if you measure those, it is always invertible then for
yeah, exactly. So if you measure a number of parameters that is 4 to the and this is for spin 1/2 particles. If you measure, if you take a measurement that is which has 4 to the n, where n is the number of spins, and these measurements are not redundant, then you can always invert the relation and write down the state as a probability distribution.
And is there no sort of locality problem with like a Bell locality that you get non-local variable, non-local measurements?
No, there's no problem. Like this doesn't violate quantum theory at all. Like everything is consistent.
So,
okay, thank you.
Do you have a last question from Max?
Yeah. So I wonder. So this is related to cubism, right? So the formulation of quantum mechanics as a quantum Bayesian theory. And so my question is, first question I want to ask is sort of, in order to do the actual measurements, you need copies of the system, right? So but you cannot really copy systems in quantum mechanics. So how do you solve that?
Yeah, so it depends on in which setting. So in the reconstruction setting, it's true, you cannot create copies, right? Like meaning that you cannot have a state and then create a copy out of it. But what you can do is you can produce experiment, measure, and then you say, I'm going to try to produce, to the best of my knowledge, the same state. And you can repeat this process on and on. And of course, in a real system, you would get different states every time, okay? Which is basically telling you that the state is not pure, right? But you can always try to repeat the experiment on and on. And then on the other aspect of this question is, do I need this for simulating quantum dynamics? And the answer is no. So what we start is with very simple product state that we can represent classically, and then we time evolve that state, right? Like, so we're never measuring the system. We're just taking that probability distribution and time evolving it according to the laws of quantum physics.
So what according to you is the actual advantage of using this representation over just using complex density matrices? Is there is it like you can use your neural network sort of toolbox directly on it without changes, or
no? Yeah, so exactly. So okay, there are several advantages and some disadvantages as well. So the advantage that I see is two. So one is you can use the neural nets as they have been designed. That's important, but not necessarily fundamental. The other thing that I think is a little bit more important is the issue that Giuseppe was discussing, right? Like that encoding the sign structure is very complicated, and there are challenges, right? So if you want, this was my biggest motivation when I started using this type of models, was because it's not that we didn't try, or I didn't try doing the complex regular density matrix representation. So I have a lot of work on that too. But what we saw is that, for systems that are really, really interesting, where these methods would make a difference if they worked, usually the sign problem is the issue, like this sign structure. So there's really, really complicated to solve problems that are unsolved, right? Like, so, and those usually trace back to the sign structure and the difficulty in imposing a good sign structure in the neural net. And so one way of doing this is, okay, just use this probabilistic representation, which is always positive, and you don't have issues with the sign. And but it also has some issues, right? Like, and the issue is the fact that not every probability distribution of the ones that I was using can be translated into a quantum state, okay? Because there may be probability distributions that correspond to a matrix that has negative eigenvalues, for instance. And so that's the tricky part about using this formulation. But nevertheless, I mean, you can still make progress, right? Like, I guess we still don't know if this is better. I'm not necessarily convinced that it is, but it's, if you want, a road that I am exploring.
Thank you.